I am bored. I discovered Desmos. I discovered the universe. I have an idea. I define the astronomical unit. I define the radius of the sun in terms of the astronomical unit. I define the radius of each planet and the equation for its orbit. I define the equations for all the orbits. I define each planet. So now there's a solar system. There's a sun at the center, accurate, not scaled, because the sun scaled to these numbers would get bigger than the Mercury's distance. The planets scaled, but all the orbits are accurate, except they all simplify to perfect circles. And I know they don't move in perfect circles. For version 1.0 of this, I don't care. I simplify, it's fine. And the planets kept their apparent difference in size because they weren't scaled with a multiple, which will make the difference bigger. But they weren't scaled. They weren't just scaled with a constant either to make the difference go smaller. But they were scaled with a dynamic number representing their relative size, as you can see here. Okay, this is quite boring and stupid. We want they should move like they do in real life. I want. And I discover sliders. Sliders in Desmos, you can have a variable, change it around, and I think of an idea like this. I define the circle with origins, a dynamic origin. Origins A and B, which A and B are defined relative to each other, being the equation for the bigger circle. So B is B equals 0, but it's a slider. You can move it. But A is equals to 25 minus B squared, which is R squared minus B squared, which is the equation for this circle. And when B gets bigger, A gets smaller, etc., etc. It fails when B is greater than the radius on either side. So I do research, meaning I ask ChatGPT, and it comes up with using trigonometry. But before we go into that, let's have a word for our sponsor. Our sponsor, the Unit Circle, is always here for you when you try to figure out trigonometry. Here's how it works, especially regarding cos and sine. This unit circle radius 1, triangle within it, hypotenuse 1. The value of cos is the value of this line here, and the value of sine is the value of this line here. Therefore, for any given triangle, the value of cos is going to be adjacent over hypotenuse, just to bring it to be a triangle in a unit circle, and sine opposite over hypotenuse. Now, the value a point on a graph AB where A is equals to cos x, B equals to sine x, x given is x will be the angle. Whenever that angle changes, that point is going to move around in a circle. So let's show it with a moving circle. Let's just get rid of these lines and let's bring out this circle here. D equals 0. What we did here is we defined D, and then A and B is cos D sine D. And this circle has origin minus A squared minus B squared equals 0.5 squared. So this is equals 0.5. And when D changes, this is going to move around. I guess 360, it's going to move around the whole way. Now, what do we want to, let's say we want we have a bigger circle and another circle like this on it. The origin of this circle is, the equation is almost going to be the same as this circle. It's the same size, let's say, but the origin is going to be minus 2a minus 2b. So when a and b has a value which is defined when d changes, the value here is going to be times 2. as it's a larger circle. So you can see that the value is going to change. The multiple of a is always going to be a multiple of the radius. If the radius is 1, then it's just a and b. If the radius is 2, like this, it's going to be 2a, 2b. Okay, so what happens if we want to move it on a different speed? Remember, a and b changes when d changes. So if we want it to change, it should go faster or slower, you just add it inside the brackets to be 2d or 1 or half a d, which is going to make it slower. So here we have a third circle, which is underneath this one with equation minus 2a1, which a1 and b1 are defined here as cos 2d. And now when we move this, it moves quicker. So back to the solar system. We're going to define d equals 0, which is going to have a slider, and d is going to represent a day. Now, for example, Earth is going to go around the hole in 365. When d will be 365, Earth is going to have returned to the same place. So we need to make sure in the equations we put a variable that when d is 365, that variable is going to be 360. Because in the variable we're going to use with cos and sine, it's 360 that goes around. So we define t equals 360 divided by 365 d, and that's going to be equals 0.863. Now, each planet we're going to substitute in their equations their own a and b, and their a and b is going to be a is going to be equal to cos some multiple of d of t, and b is going to be sine some multiple of t. And the multiple of t for Earth is going to be just t, cos t, sine t, because that's a unit circle here. But for all the other planets, it's going to be the multiple of t in the cos and sine is going to be 365 divided by the days of their given year. So, for example, Mercury has 88 days. In their equations, it's going to be 365 divided by 88. So that will ensure that the smaller planets move quicker and the larger planets move slower, like it's in real life. It will represent how long the year is for each and every planet. So let's just put all the equations in. Now that we have the equations, we're just going to substitute and edit the equations of all the planets, and we're gonna add here the given a and the given b for the y, and obviously we multiply it by m2, which is the radius, as we have seen earlier. At the unit circle for Earth, it's going to be 1. E2 is 1 essentially, but for the others, it's going to be a multiple, and this should work. All the equations are done, and it's time to try out our solar system. Let's start with the inner planets. Let's go to D, which is day. Let's start from 0 to, let's say, 1,000 for now. And let's move it. And it's on radians, so we need to change it to degrees. And now it should work fine. And let's start slower, so let's put here like 500, just so the increments of the mouse is slower. So as you see, as days go past, Mercury, if you put an 88 here, 88, Mercury's year. Put in 225, Venus's year. 365, Earth completed the year, and the others, Mars is still in the middle. So let's just move around a bit, play around a bit. They all go around, as you can see. And the same to the outer. they barely moved. They move much slower, much slower. A year for Venus, a year for Neptune is 60,000 Earth days, something at that range. As you can see, it is around. It almost came back to the same place. Jupiter's is 4,333. Jupiter has completed 1 year, and so forth. This is all the planets and moving. Now, of course, the next step is going to be to build a moon, which is very easy, and it should move basically. It's going to be 365 divided by 29.5, and the radius of it. I made it already. It's just with this scale, the moon will end up within Earth with this scale. So, but that's also cool. And quickly, I'm going to show what I did in 3D because it's not very good, the 3D graphing situations. I haven't found a good one to make all of this, but I created the 4 inner planets I created just to show with the same thing. So you see the orbits of the 4 planets in 3D, and that is what version 1.0 is. Version 1.2.0 maybe will have the accurate elliptical circles, and maybe they're going to actually be defined in terms of Newtonian equations and gravity and so forth.